if the electrode gets negatively charged with respect to the solution, that is the electrolyte, that is oxidation potential. The bubbles you can see, that will be hydrogen gas, right? So yes, H plus electron will give you half H2. So that will be the cathodic reaction. So whichever is having high reduction potential, that will be preferred as cathode, and which is having high oxidation potential or low reduction potential, they will act as anode. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidyashram School of Excellence, Mysore. So today we are back with session 2 of the chapter Electrochemistry. So in last session, we discussed about what is electrochemistry, right? The introduction, and then we studied about redox reactions, right? An introduction and a quick revision about redox reaction, right? Yes, and then we studied about electrochemical cell, right? In electrochemical cell, what energy is converted into what energy? Yes, a chemical energy is getting converted into electrical energy, right? And then we studied in detail about Daniell cell, right? Which all reactions are happening in the anode and cathode, right? Yes. Now, representation of the cell also we studied in last session. Okay. So, in today's session, we are going to study about electrode potential. Yes. And then standard hydrogen electrode, then electrochemical series, and then last we will be studying about Nernst equation. So, beginning with the first one, that is electrode potential. Okay. So, you might be familiar with the word potential. Okay, where is this potential difference developed? Okay, you might have studied already this in physics. Okay, so let's take in this case, I am taking a beaker in which I have electrolyte, that is, let's consider zinc sulfate, ZnSO4. Okay, and then I have dipped in here a rod of zinc. Okay. Right? A zinc rod is dipped in its own salt solution. Zinc is dipped in zinc sulfate solution. If I have taken copper, I dip copper rod in copper sulfate solution. I told you this zinc rod, it is called as electrode, right? So, zinc electrode is dipped in zinc sulfate solution. If it is copper, copper electrode is dipped in copper sulfate solution. So, this is the first thing that you have to understand. That is, the electrode is dipped in its own electrolytic solution, its own salt solution, right? So, zinc is dipped in zinc sulfate solution. So, we know that what a reaction takes place here, right? We have studied this. Yes, zinc undergoes oxidation and it oxidizes to Zn2+, right? We know that. So, the electrons will be present in the rod. So, the electrons will be present inside the electrode, right? And we know that the electrolytic solution is of ZnSO4. So, yes, there will be Zn2+ ions which will be present inside the electrolyte, right? So, what you can see inside the rod, there will be, inside the electrode, there will be a negative charge, and outside of it, the Zn2+ ions will be accommodated. Okay. So, inside the electrode, there will be electrons and outside of it will be Zn2+. So, you can see a charge difference there, that is a potential is developed there. See, there is negative charge in here and outside that a positive charge is also developed. Yes, so that means a potential difference will be there, a potential will be developed, right? So that is called as electrode potential. So we were talking about a single electrode potential. Only one electrode was there, right? Zinc was dipped in zinc sulfate solution, right? So the electrons and the Zn2+ amongst them a potential was developed, right? So that is called as single electrode potential. So let's see, when an electrode is dipped in an electrolyte, the electrode acquires a positive or negative charge. Okay, the electrode can acquire either a positive or negative charge. With respect to the electrolyte, the potential difference developed is known as electrode potential. Because there is a positive and negative charge there will be a potential which is developed, that is called as electrode potential, and that can either be a positive or negative value. Okay, right. Now, oxidation potential, electrode is negatively charged with respect to solution. If the electrode gets negatively charged with respect to the solution, that is the electrolyte, that is oxidation potential. Okay, you will get a negative value. Now, reduction potential, the electrode is positively charged with respect to the electrolyte. Electrode is positively charged. So, if the electrode is getting positively charged, that is reduction potential. Clear? Now, it is not possible to measure the potential of a single electrode. Yes, only the potential difference between two electrodes can be measured experimentally. So, this is one single electrode, right? Zinc dipped in zinc sulfate solution. It's about a single electrode. So, what it is given here? We can't measure the potential of a single electron. It has to be connected with some other electrode, and the potential difference between these two half cells or these two electrodes had to be measured. Right? The potential of the single electrode can't be measured, or it's always the difference of potential between two electrodes that can be measured, right? Okay, so the single electrode potential depends upon which are the factors? Yes, it depends on the concentration of ions in solution. The concentration is more or less, it depends upon that. If you have taken 1 molar concentration solution, 2 molar, all those it depends, right? Next one is tendency to form ions. How easily it can form ion, how easily it can get oxidized, right? Next is temperature. It also depends on temperature. So what is this? The single electrode potential depends upon these three factors. So I hope you are clear with what is electrode potential, right? So in the electrode, there will be a negative charge, and outside it, positive charges will be there. So as there is a charge difference, a potential will be developed. That is called as single electrode potential. Okay. Now, let's understand what is standard electrode potential. We studied electrode potential. Now, we are going to study what is standard electrode potential. Yes, standard, under standard conditions. Okay, let's see. The standard electrode potential may be defined as potential developed when an electrode is in equilibrium with its own ions at 1 molar concentration at 298 Kelvin and 1 bar pressure. Okay, so let's take the same example that we have taken before. There is zinc sulfite which is taken as the electrolyte, and there is a zinc electrode as well dipped in it. Okay, but the electrolyte solution now in the standard electrode potential, that means electrolyte will be having 1 molar concentration and the pressure will be 1 bar and the temperature will be 298 Kelvin. Under standard conditions, when we calculate the electrode potential, that is called as standard electrode potential. So what are the standard condition? 1 molar concentration, 298 Kelvin temperature and 1 bar pressure. Okay, I hope it is clear. Now coming on to electromotive force or EMF of the cell. Okay, electromotive force or EMF. Even this you are quite familiar with in physics, right? So how do you calculate the EMF in case of the cell? Let's see. Okay. The cell potential difference between the two electrodes of the cell when no current is drawn through the cell is called as EMF. So to understand about this, I hope you remember when we discussed about Daniell cells, there were two half cells, right? And this connected together, and they were connected together by a wire. There was a connection as well, right? And then we studied about how the electrons are flowing and in which direction the current will flow. All those were being discussed, right? So what did we study in Daniell cell? There are two beakers in which the electrodes were dipped, and those two were called as half cells, right? And which together comprises the cell. Okay, so what is actually the EMF or the electromotive force? It will be the potential difference between the two electrodes. Okay, so to understand this, I have taken here zinc sulfate solution, right? The electrolyte, and then there is a zinc rod here, right? And let's take another half cell, right? Another half cell, that is copper sulfate. Okay, the electrolyte is copper sulfate and I have dipped a copper electrode in here. Okay, and then I have connected it through a wire. Okay, I have kept a voltmeter also. I have connected it through wire. Okay, so this is what we have studied about Daniell cell, right? So how do you calculate EMF of the cell? We are not talking about single electrode, we are talking about the cell. So how do you calculate the EMF of the cell? It will be the difference between this electrode potential and this electrode potential. Clear? Yes, we studied about single electrode potential, right? So the potential developed here minus the potential developed here will give you the EMF. So what it is? E cell will be equal to E cathode minus E anode. Okay, so the potential developed in the cathode minus potential developed in the anode. So in the case of Daniell cell, we know that which is the cathode? It's a copper electrode, right? Copper is the cathode. So the potential of this one, that is E of this cathode minus E of anode, will give you E cell, that is electromotive force of the cell. Okay, that is also we can call it as cell potential. Okay, one single electrode, it's called an electrode potential. For a cell, it will be called as cell potential, right? Okay, also it can be written as E right minus E left. Okay, so what you have to remember, whenever you are representing the cell, the cathode will be on your right side and the anode will be on your left side. Okay, so in the case of Daniell cell also, the cathode is in the right, copper is in right and zinc is on the left, that is anode, right? So the right minus left, that is E of the right cell minus E of the left half cell will give you, yes, the EMF. Clear? So you can represent it in either form, that is E cell is equal to E cathode minus E anode or E right minus E left. Okay, so E right minus E left, you have to remember cathode will be always represented on the right side. Okay, yes. Now the standard electromotive force, the same way we discussed potential, electrode potential and standard electrode potential, same way EMF and standard EMF. Now what is that? It is the potential difference between two electrodes of the cell under standard conditions, that is 298 Kelvin, 1 molar concentration and 1 bar pressure. So same standard conditions, if you are taking the E cell, if we are calculating the EMF of the cell under standard conditions, that means here in the zinc sulfate and copper sulfate, I have taken 1 molar concentration. The temperature is 298 Kelvin in each of this half cell and the pressure is also 1 bar. Then the EMF that I am obtaining will be standard electromotive force. I hope it is clear. Right. Now when we were discussing about electrode potential, it was discussed that yes, the electrode potential or a single electrode potential can't be measured and we can only calculate the difference, right? E cell we can calculate, that is E cathode minus E anode, but we can't measure the electrode potential of just the cathode or just the anode. So for that we use something which is called as standard hydrogen electrode. Okay, so to measure the single electrode potential of any of the electrodes, we can use this, that is the SHE, standard hydrogen electrode, and calculate the electrode potential of those electrodes. Okay, so now what is the importance or what is the speciality of the standard hydrogen electrode is that it can act as both anode and cathode. Okay, yes. So let's see. SHE, it's in short form, it is written as SHE. It is a reference electrode used for calculating the electrode potential of different electrodes. Okay, so it is used to calculate the electrode potential and it is used as a reference electrode. So it is used as a reference electrode means the potential or the electrode potential of SHE will be 0 volt. Okay, it is considered as 0. Right. Now the electrode potential of SHE is assumed to be 0, right? And then SHE can be represented as follows. So this is the representation for SHE, that is standard hydrogen electrode. So let's see the construction of SHE now, that is standard hydrogen electrode. So there will be a platinum electrode here. As you can see here, this is the platinum electrode. There will be a platinum electrode and surrounding to it, that is it will be surrounded or coated by platinum black. Okay, and the electrolyte solution here which is taken, it's 1 molar HCl. Okay, it's an acidic solution. What it is? 1 molar concentration of HCl is taken as the electrolyte and there is a platinum electrode which is coated by platinum black. Right, and here you can see a small opening is there through which hydrogen gas is bubbled into this. Okay, H2, what is H2? It is hydrogen gas at 1 bar pressure. Through this hole or this gap you can see here, it is bubbled inside so through that the hydrogen gas is bubbled inside. Okay, I hope it is clear. The diagram it is clear. So as I said, SHE can act as both anode as well as cathode, right? So half cell reactions, in case if it is acting as anode, okay, acting as anode means what? Right, oxidation takes place. I told you always in the anode oxidation takes place and the In the cathode, reduction takes place, right? So, in the case of anode, if she is acting as anode, yes, hydrogen gas will get oxidized to H plus ions. Right, hydrogen gas that is bubbled into it, once it reaches here, as you can see this will be H plus ions. It gets oxidized into H plus ions. Okay, so that happens when it is acting as anode. Now coming on to the next one, if it is acting as cathode, what happens? Reduction takes place, right? So now the H plus, that is, where is the H plus present? In the electrolyte, right? Because what we have taken HCl solution, that is HCl is the electrolyte. So the H plus ions will accept the electrons and what will be bubbled out? Yes, the bubbles you can see, that will be hydrogen gas, right? So yes, H plus electron will give you half H2. So that will be the cathodic reaction. So as you can see here from the reaction as well, it can act as both anode as well as cathode. Both of this reaction takes place in this sheet. Okay, so it can act as both anode and cathode. So in the anode, oxidation takes place. Hydrogen gas is getting converted into H plus ions, oxidized into H plus ions. And when it is acting as cathode, yes, the H plus accepts the electron and gets converted into or reduces into hydrogen gas. Okay, so this is the construction of She. Okay, and as I said, it is used as a reference electrode to calculate the electrode potential of different electrodes. Okay, so She is clear. Now how, with the help of the standard hydrogen electrode, we can calculate the electrode potential of different electrodes? Let's see. Okay, so first we have taken, as you can see, copper sulfate is here. Okay, copper sulfate, yes, and a copper electrode is here. Okay, and in this case, we have taken the standard hydrogen electrode. Okay, so what is the reaction that is taking place in anode? Okay, so in this case, we know that copper electrode undergoes reduction, right? Copper undergoes reduction. So what happens in the anode? What is happening? Now my She is acting as anode, right? So what happens? Half H2 is getting converted into H plus an electron, right? Yes, hydrogen gas is getting oxidized into H plus. And in cathode, what reaction is taking place? In cathode, what reaction is taking place? Right? Cu2 plus accepts this electron and forms Cu. Right? Yes, this is the reaction that is taking place in anode and cathode. Okay, so how do I calculate the E cell? Okay, I have to calculate the E cell. Right? So E cell will be equal to E cathode minus E anode. We studied this now. Right, E cathode minus E anode. So what is in the cathode? What is the reaction taking place? E of Cu2 plus bar Cu. This is how we represent it. Cu2 plus is getting, it is reduced to Cu. So I write Cu2 plus bar Cu. Okay, minus the electrode potential of my She. Right, yes, electrode potential of She. And what is happening there? H2 is oxidized to H plus. Right. So what did we study? What is the potential of standard hydrogen electrode? It is considered to be 0, right? So that means E cell will be equal to what? E cell will be equal to the electrode potential of copper, right? Because this part is 0. So that means whatever, once you connect these two, you get the cell potential. That is, for the whole of the cell, you get the potential, which will be actually equal to the electrode potential of copper, because electrode potential of She is considered to be 0, right? So whatever you are getting the value for the potential of the cell, that will be equal to the potential of the, that is electrode potential. So I hope this is clear. Now coming on to when it is acting as cathode, let's take this example in which you can see here ZnNO3, zinc nitrate, is taken as the electrolyte and the electrode here is zinc. Okay, now zinc is acting as the anode. Zinc is the anode here. Now in that case, again we have taken She, which is the cathode in this case. Okay, so in that side you can see that is the cathode. She is taken as the cathode, right? So what reaction is taking place in the anode? Anode, what is taking place? Oxidation, right? Which among these is undergoing oxidation? Zinc, right? Zinc gets oxidized into Zn2 plus and 2 electron. right? And in the cathode, what will happen? Always in the cathode, reduction takes place. In the anode, oxidation takes place. Okay. So, once it acts as, that is the sheave, if it is acting as cathode, what is the reaction? H plus will be accepting electrons and giving half H2. So, these are the reaction taking place. Okay. So, as I said, how do you calculate E cell? It will be equal to E cathode minus E anode. Right? E cathode minus E anode. Now, what is the cathode here? It is the sheave. Okay. So, we know that the EMF of the standard hydrogen electrode is 0 minus what is happening here? It is E Zn bar Zn2 plus. That is what is happening, right? So, E cell will be equal to what? Minus E Zn bar Zn2 plus. So, this is what you will be getting. Yes, as you can see here, the voltmeter is showing the reading 0.76. So, that actually what is showing here is the potential of the cell, which is actually equal to the potential, electrode potential of the zinc. Right. So, this way I hope you understood that she can act as both anode and cathode and how it can be used to calculate the electrode potential of different electrodes. Right. So, let's move on to the next concept, that is electrochemical series. Okay. So, as you can see here in the electrochemical series, the elements will be arranged in the decreasing order, of reduction potentials, in the decreasing order of reduction potentials, okay, or if it is in the decreasing order of reduction potential, that means it will be in the increasing order of the oxidation potential. So, you can see from fluorine to lithium, if you are moving down, yes, the reduction potential decreases. So, who is having the highest reduction potential here? It will be fluorine. So, the value, as you can see here, it will be positive, that is plus 2.87. Right. Okay. So, on the top, you can see all of this are having positive values. And as we move down, yes, you can see for hydrogen, okay, for hydrogen, the value is 0. We just studied now. For the standard hydrogen electrode, that is for hydrogen, what is the value? It is 0. The reduction potential value is 0. Then as we move down below the hydrogen, yes, you can see the values will be negative, right? So, they are having the least reduction potentials. So, I hope you understood as we move down the series, right? This is the order in which the reduction potential, that is in the decreasing order. Okay. So, what exactly is the use of this electrochemical series? It is that, yes, whichever is on the top, as they are having highest reduction potential, they will be preferred as the cathode. Okay. So, if two electrodes are present, which will act as cathode and which will prefer to be acted as anode, it will be based on their reduction potential. So, if they are having high reduction potential, yes, that is they are having positive value or high reduction potential value, that means they will act as cathode. Okay, and whichever is having high oxidation potential value, that will act as anode. So, high oxidation potential values, that means those having less reduction potential, right? So, as you can see, those who are having this negative values, they will be preferred as anode. So, from electrochemical series, we will be able to understand which one will be cathode and which one will be anode. So, whichever is having high reduction potential, that will be preferred as cathode, and which is having high oxidation potential or low reduction potential, they will act as anode. Clear? Yes. Now, the reactivity of metals increases on moving down the series. As we move down the series, the reactivity of these metals will keep on increasing. Okay? Yes. Now, the electropositive character of metal increases on moving down the series. Even the electropositive character increases. So, as we move down the group, the electropositive character also increases and the reactivity also increases. Right. Now, a redox reaction is feasible when the substance having higher reduction potential get reduced and the one having lower reduction potential get oxidized. Okay, higher reduction potential whichever is having, that is a redox reaction, will be feasible. This reaction will take place when the higher reduction potential whichever the electrode is having that should undergo reduction. That means that should act as cathode, right? Where reduction takes place in the cathode, right? So, higher reduction potential whichever is having, that must undergo reduction. That means that will act as my cathode, right? Okay, and the redox reaction will be feasible if the electrode having higher oxidation potential will undergo oxidation, and that will act as anode. Okay, so I hope the importance of electrochemical series is clear for you. Right, now moving on to the next important topic of the chapter, that is Nernst equation. Okay, so it is used to calculate the potential when concentration of the solution is not unity. So as we were discussing till now about the electrode potential and how we will not be able to calculate the single electrode potential. So what did we use? Standard hydrogen electrode. Okay, so till now we were discussing about standard conditions. But if my electrolyte is not present in standard condition, that is 1 molar concentration, 298 Kelvin, 1 bar pressure, if it is not under standard conditions, will I be able to calculate the electrode potential? Yes, that will be based on the equation which was developed by Nernst, which is called as Nernst equation. So let's understand the equation. So let's consider the reaction that is happening. Mn plus an electron gives M. Okay, that is, it is raised to the power n plus, the charge is n plus there, and it accepts n electron. That is what reaction is happening there. Reduction is taking place, right? We are talking about reduction potentials, right? Reduction is taking place. So n plus charge was there. It accepted n electrons, underwent or undergone reduction and formed M. That is our metal. So this is the general equation. Yes, so this is the Nernst equation. How you can write it? E, the reaction that is taking place. What is happening? Reduction is taking place, right? E Mn plus slash M is equal to E naught of the reaction. E naught means under standard temperature pressure conditions. That is 298 Kelvin, 1 bar pressure and 1 molar concentration. Under standard condition, what did we call this? Standard electrode potential, right? So E electrode will be equal to E naught electrode. That is standard potential minus RT by NF ln M by Mn plus. Okay, so R stands for universal gas constants, T is temperature, N is the number of electrons involved, and F is called as, yes, Faraday's constant. F is called as Faraday's constant. 1 farad will be equal to 96,500 coulomb. Okay, so this will be important in your numerical. So 1 farad is equal to 96,500 coulombs. Right. Now the concentration of the solid is taken as unity. As you can see, the concentration, the square bracket represents the concentration, right? So it is on the numerator, M is there. So for solids, the concentration is considered as 1. Okay, so how does the equation become? E will be equal to E naught minus RT by NF ln 1 by Mn plus. This becomes 1, right? Because we are considering for solids the concentration to be 1, right? So yes, E is the reduction potential of the electrode. That is, this is the reduction potential. E naught is the standard reduction potential. R is the universal gas constant. T is temperature. N is the number of electrons involved. F is Faraday's constant, which is 96,500 coulomb, and then Mn plus will be the concentration of the Mn plus ions present. Clear? So this is the equation. Right. Now how we can further develop this, let us see. So now we are converting the natural logarithm to the log base 10. Okay, so to convert that, what we have to do? We have to multiply it by 2.303. So the equation becomes, as you can see here, so the equation was E electrode is equal to E naught of electrode minus RT by NF ln 1 by concentration of Mn plus, right? This was the equation. Now I am converting this ln into, that is natural logarithm, into log base 10. So I have to multiply it by 2.303. So my equation becomes like this, that is E electrode will be equal to E naught. E is equal to E naught minus 2.303 RT by NF log 1 by Mn plus. So this changes to log now because I multiplied by 2.303. Clear? So this is the Nernst equation. Okay. So this is under any concentration. It's not under standard temperature or pressure. Okay. So now we are going to substitute the values. So now 2.303 is here. R we are going to substitute as 8.314. Temperature is 298 Kelvin. N we are keeping it as it is. It depends upon the reaction, the N changes, right? And F also we know what is the value, 96,500. So how the equation becomes, E electrode will be equal to E naught of electrode minus 2.303 into 8.314 into 298. Okay, we are taking all the standard values, right? Divided by N. N I don't know. It's based on the reaction, right? Into 96,500. And what is left? Ln log 1 by Mn plus, right? Concentration of 1 by Mn plus. So this is the equation becomes like this. So if I calculate all of these values, I get it as 0.059. Okay, so my equation becomes E electrode is equal to E naught electrode minus 0.059 by N log 1 by Mn plus. Clear? Right? So if I do all of this calculation, I am getting this value. So if the question asks you to calculate the electrode of the potential of the electrode, you can use this particular equation if it is under standard conditions. That is 298 Kelvin, temperature is 298 Kelvin, Farad you can use 96,500 and all those values you can substitute. Instead of writing all of that, you can just use this value. If it is under standard condition, 298 Kelvin, if it is under 298 Kelvin, you can use this particular equation. Clear? Now moving on to the next part, if you are taking a general equation that is AA plus BB is giving CC plus DD. Okay, where the small a, b and c, d are the stoichiometric coefficient or the number of moles, right? And the capital A, B and C, D, A and B are the reactants and C and D are the products, right? Okay, so in that case, how do you write the Nernst equation? Okay, in this case, how do you write the Nernst equation? E cell will be equal to E naught cell minus RT by NF ln. Okay, we are first writing in the terms of natural logarithm. The same equation ln, and now this part will be on the numerator and this part will be on the denominator. That is product on the numerator and the reactants on the denominator, right? So this way you can write, and which is raised to the number of moles. Okay, so concentration of C raised to the power C, concentration of D raised to the power of D. Yes, this number of moles or the stoichiometric coefficient will be present as the power, right? So this way you can write it, right? Now this natural logarithm, again if I want to change it into log base 10, how do I change it? Multiply by 2.303. So the equation becomes E cell is equal to E naught cell minus 2.303 RT by NF. So it becomes the log of the same thing. So in general, if I know the concentration of the ions present in the anode and cathode, I can use this particular equation, that is E cell is equal to E naught cell minus 2.303 RT by NF log of anode by cathode. It is anode by cathode. The concentration of the ions in the anode minus the concentration of the ions in the cathode. So this is the equation that you can use. Okay, if you know the concentration of anode and cathode. Okay, right? So I hope the different forms of Nernst equation is clear for you. Okay, right? And in the next session, we will be discussing about the thermodynamics of Nernst equation. How it is related to the thermodynamics we are going to see. Yes, it can be related. The Nernst equation can be written in forms of Gibbs free energy. How you can calculate all those related to thermodynamics we will be studying in the next session. And then we will be moving on to the next type of cell, that is electrolytic cell. Till here we were discussing about electrochemical cells, right? Now we will discuss about, or we will study about electrolytic cell. Okay, so I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.